Hello and welcome to the second in the series of 6 films about the standard level equilibrium topic. Here we're going to be looking at things called equilibrium constants, and hopefully by the end of this film you'll be able to write an equilibrium constant expression for a homogeneous equilibrium system, and hopefully you'll also understand what the size of an equilibrium constant tells us about the position of equilibrium. Now the position of equilibrium is something we talked about in the previous film, so hopefully you've seen that one and this will make sense to you. If not, then my advice would be to watch that first film before you watch this one. Okay, now what we said in the previous film was that for any system to be at equilibrium, we're going to have a reversible system where the reactants can turn into products and the products can turn back into reactants. And the first thing to say about an equilibrium constant, apart from the fact that it is always given the symbol K, capital K, is that it's equal to the concentration of the products divided by the concentration of the reactants. So if ever we write something in a set of square brackets in chemistry, this reads as the concentration of whatever's in the square brackets. Okay, so I could read this as the equilibrium constant is equal to the concentration of the products divided by the concentration of the reactants. However, it is just a little bit more complicated than that, and that's because we have to pay attention to how many of the reactants and products there are in our equation. So if I look at this system here, where A and B are turning reversibly into C, what you can see when I've written the equilibrium constant expression is that K equals the concentration of C divided by the concentrations of A and B. But notice I'm not adding these concentrations, I'm multiplying them together. So we'll never see any addition signs in these expressions. They'll always be multiplications. And what is more, if you've got some stoichiometric coefficients, that is to say some numbers in your equation that talk about the number of moles reacting of each substance, then we have to do something with these numbers when we come to write our equilibrium constant expression. So here we've got B and C in the products, so they're on the top of our equilibrium constant expression. A is our reactant, so it's at the bottom. But notice that because there are two A's in the equation, we square the A term, and because there are three C's, it's the concentration of C cubed. So this would read as the equilibrium constant for this reaction is equal to the concentration of B multiplied by the concentration of C cubed divided by the concentration of A squared. Okay, so that's what equilibrium constant expressions look like. If you're asked to write an equilibrium constant expression, you're simply writing K equals and then putting the reactants and the products in your fraction the right way round and with the correct powers. What you've also got to be able to do is to consider what an equilibrium constant tells you about the position of equilibrium. Now, if you think about this, these are these diagrams that we saw in the first film. In reaction system 1, we could say that the concentration of products is large, but the concentration of reactants at equilibrium is quite small. Now if that's the case and this top number is large and this bottom number is small, then the value of the equilibrium constant will be greater than 1. In this reaction system here, where the amount of products is small, so the top of our fraction is small, but the concentration of reactants is relatively large, so the bottom of our fraction is large, then the value that our equilibrium constant will take will be small. It will be less than 1. Okay, now we're not in the business at SL of calculating the values of equilibrium constants, but what we are expected to know is what the value tells us about the position of equilibrium. And there's only two situations we need to worry about. And that is when K is much less than 1 and when K is much greater than 1. And as we've just said, if you've got an equilibrium constant that has a value of much less than 1, then the concentration of reactants compared to the products must be relatively large. In other words, the fraction is small, the fraction is less than 1. If we've got a K where K is much greater than 1, then the concentration of products has to be large in comparison with the concentration of the reactants, because any time we write an equilibrium constant expression, the products are on top and the reactants are on the bottom. So really all we need to be able to do with equilibrium constants in the SL course is to be able to write expressions for them and to be able to say something about the position of equilibrium based on the size of the equilibrium constant. So if it's very small, the concentration of reactants is large and the position of equilibrium is to the left. If the equilibrium constant is large, greater than 1, then the concentration of products is large and the equilibrium position is to the right. So nothing too complicated there, I hope. Hopefully you feel like you can write equilibrium constant expressions for homogeneous equilibrium systems. They're the only ones you're going to see, so you don't really need to understand what homogeneous means. It just means that everything's in the same state. So it's all liquids or all gases. And you can say something about the position of equilibrium when you see the size of an equilibrium constant. If you've got any questions or comments, then the sooner you get them answered, the better for you. So feel free to come and see me or to post a comment on YouTube.